Good evening. Welcome to our fourth and final lecture in our 2013 spring series. It's good to see so many of you back again. A lot of you I know have been to all four. We really appreciate that. And I appreciate a lot of the feedback I've gotten in terms of the series. We're still planning for next year, so I don't know where we will be. We may be back here. We definitely won't be at the Huntington. That one won't be available for another 2 years. So, but hopefully, if you are on our mailing list, the Carnegie mailing list, then you will get a brochure and you'll know where we end up next year. So those of you who were here last time heard a little bit about stellar evolution, that is the lives of stars. And I'm assuming, I was in Chile, so I don't know, I'm assuming that you heard a little bit about how stars create elements, at least some elements. Tonight you're going to hear kind of a continuation of that about rare elements. These are elements that are not formed in the way that Jeff probably talked about last time. But these elements are very important for everyday life for many reasons. And tonight's speaker, Ian, who is a Carnegie Fellow, he's now been at Carnegie 3 years after getting his PhD at the University of Texas, works on these rare elements. That is how the universe makes elements, many of which I never hear of. He talks about these elements, and I'm like, that's an element, I've never even heard of this. But he's trying to understand how the universe creates these things. So tonight you're going to get a very special treat. He's going to focus on, I believe, probably uranium, but we'll find out in a minute. So let's please welcome Ian for our final lecture in the series.
When you look at the stars, what do you see? Do you see cosmic alchemy in action as each star forges light atoms into heavy ones through a myriad of fusion reactions? Do you see each star as a unique chemical fingerprint, holding within it a memory of generations of stars long before? Do you see limitless sources of energy as each star provides for its system of planets and any civilizations that may inhabit them, whose citizens may also be staring up at the universe overhead, enamored by that energy and asking questions of nature? In 1936, British chemist Francis Aston was giving a lecture, and he was discussing the possibilities for our own species, for extracting some of this energy from atoms. And here's what he had to say. We cannot prevent them from doing so, and we can only hope that this knowledge will not be used exclusively in blowing up one's next door neighbor. Aston had recently built the first mass spectrometer. So this is an instrument that you use to separate atoms that have the same charge but different mass, isotopes. And during his investigations of different elements with this new instrument, he had discovered what was perceived to be a defect in the measured masses of different atoms. In other words, the mass of 4 hydrogen atoms added up to exceed the mass of 1 helium atom by 0.7%. But this was no defect. This is the energy that powers stars. Now, hydrogen, the lightest atom, just a proton and a single electron. Hydrogen is by far the most common element in the universe. Meanwhile, far at the other end of the periodic table, there's another element, 1 trillion times less common than hydrogen. And this other element can also be exploited to recover that marginal excess of energy, uranium. Our quest to extract this energy from uranium would drive a secret military-industrial complex that rivaled the scale of the entire American auto industry. It would bring about unspeakable tragedy, hasten the end of the Second World War, and shape global politics for generations to come. Before we get into all of that, let's spend just a few minutes introducing what we're going to talk about. Now, I don't doubt that there are some of you who actually know a lot more of that history than I do. So that's not what I'm going to talk about much. Some of you maybe even lived through or influenced some of those early scientific breakthroughs and political decisions that were so formative. What I'm going to talk about tonight is mostly on the astronomical side of things. Where does uranium come from? What happens to it out there in space? And how did it end up here on Earth, capable under the right conditions of unleashing energy, the likes of which civilization had never seen before? So let's get to some of the atoms that will feature prominently in this story. Uranium in the Earth's crust is made up of 99.27% uranium-238 and less than 0.73% uranium-235. So less than one atom out of every 100 atoms of uranium that we find on Earth is in this lighter isotope, 235. If you take an atom of uranium-238, the heavier one, the more common one, and you hit it with a low-energy neutron, it may absorb or keep that neutron. And the atom that is produced, uranium-239, will shortly undergo a couple of transformations, turning into a different atom, plutonium. And that plutonium itself will then happily sit, mostly quietly, on a laboratory shelf for the next few tens of thousands of years. When an atom of the other uranium isotope, 235, the lighter one, the less common one, when that is hit with the same kind of neutron, something different happens. It may also absorb or keep that neutron, but the atom that is produced, uranium-236, it finds within itself an extra amount of energy. And it was more energy than was found in the previous case. And it's just enough extra energy to cause that atom to fission or split. And that fission reaction produces two lighter atoms, several energetic photons, and 2 or 3 neutrons. If any of these neutrons are captured again on another uranium-235 atom, then the process can repeat itself over and over again. And once this chain reaction gets going, there are basically only 2 ways to stop it. Now, the first, you can just cut off the supply of neutrons, just like you would choke off the supply of oxygen to a fire. The other way is to separate, violently separate, the atoms and everything else in the vicinity. Now, we know what that means. But in 1939, scientists in Europe and the United States had just come to understand this reality. What had been predicted in the abstract was now very real. The discovery, using just micrograms of uranium in a laboratory under controlled conditions, they had discovered that the lighter isotope, the rare isotope of uranium, 235, that was the one that really sustained the chain reaction. So scientists in the United States who were aware of this discovery got very worried. They were afraid that this discovery might find its way into sinister hands. And they were worried that their colleagues in Germany may have already made a discovery like this, and in perhaps pressure from the Nazis had initiated a program to manufacture a device that would actually sustain that reaction in deliverable form. So these scientists, who included some of the most prominent physicists of the 20th century, Albert Einstein, Leo Szilard, Eugene Wigner, and others, they lobbied the United States government to begin its own program to manufacture a device like that. But it was no easy task to actually engineer that device. One of the most difficult challenges was in producing a sample of uranium-235 that had concentrated quantities of the 235. During that chain reaction, the heavier isotope, 238, it doesn't play any direct role. All it does is swallow the neutrons and snuff out the reaction. So you need a concentrated quantity of 235. And the early designs for this used an average enrichment of 235 to about 80%. So if you remember the fraction that 235 occupies in ordinary rocks on Earth, you'll know that we have to increase that fraction of 235 by about 100-fold over ordinary uranium. And that enrichment process was a necessary task, but it was a major bottleneck in the process of manufacturing this device. And within a few years, secret U.S. government plants near Oak Ridge, Tennessee, had begun the process of separating natural uranium into concentrated quantities of 235. Their explicit goal was to produce a practical military weapon. But what if the separation was not a slow process, one that required several years' time to produce sufficient quantities of the 235? Or what if nature had provided that cruel head start on the uranium isotope separation, just with a different isotope mixture on Earth? Then the course of human history may have unfolded quite differently. Why does uranium exist on Earth with the isotopic proportions that it does? Now, nuclear physics, which governs the inner structure of atoms, nuclear physics has a say in this, but the answer lies mostly with the stars. Now, those of you who have been coming to this lecture series for a long time, or maybe just this season, you know that the universe is not a static place. New stars form within dense gas clouds, the stellar nurseries of galaxies. Old stars die in violent explosions. Small galaxies accumulate gas and merge to form large galaxies, which themselves cannibalize even more small galaxies before joining large groups or clusters of thousands of galaxies. Black holes form and grow, the pearls in the centers of large galaxies. Planets of all sizes are born. Perhaps some of those planets even develop life forms that evolve into sentient beings, capable of asking questions of and harnessing nature. We can only hope that they are interested in more than just blowing up their neighbors. Let's go back in time. More than 13 billion years. Just a couple 100 million years after the Big Bang. Now, the universe was a very different place. It was smaller, to be sure, but there were no stars yet, and certainly no galaxies or planets either. Only 3 elements existed. Lots of hydrogen, modest amounts of helium, and just a dusting of lithium. These, the 3 lightest elements, these were the products of the Big Bang. And that's all the universe would have ever known were it not for stars. But here and there, in dense pockets of molecular hydrogen gas, here, the first stars that the universe had ever known turned on. They lit up their surroundings, and much like celebrities, they burned bright and fast, fusing the hydrogen in their cores into helium, carbon, oxygen, neon, magnesium, and so on. In the blink of a cosmic eye, no more than a few million years later, the lives of these first stars ended in spectacular fashion as supernovae. And it's quite possible that not one of those first stars has survived until today. Now, these explosions would have scattered the newly formed carbon, oxygen, neon, and magnesium, as well as a collection of heavier elements that were actually created during the explosion itself: calcium, titanium, chromium, iron, nickel, and everything in between. All of these would have been scattered by those explosions back out into space. These were the first heavy atoms the universe had ever known. And suddenly, the chemistry of the universe changed forever. New molecules, new grains of dust were able to form. And the minuscule trace of carbon and oxygen allowed the clouds of hydrogen to collapse, to form a new kind of star, a small star. Now that's important because small stars, like our sun, they don't burn as bright or as fast. In fact, some of the stars born from the ashes of that very first generation of stars, some of those stars are still out there today. When a star is born, it locks up a chemical record of the dust and gas at that unique place and moment in the universe. The chemical makeup of stars is as unique as your fingerprints or DNA. But just like our own DNA, the chemistry of these stars retains a memory of all those stars that have lived and died before. Stars remember where they were born. As more and more waves of star formation swept across the universe, billions and billions of new stars recorded the chemical fingerprints of their surroundings. Now, some of these stars continue to shine today, but some died many billions of years ago. And with each stellar death, new atoms of heavy elements, forged from a seemingly bottomless supply of hydrogen, these would have been flung out into space. With each new generation that formed from those ashes, they would have a few more heavy atoms than the last. And these thousands of stellar generations can be found in our night sky. Enter the field of stellar archaeology. Like the archaeologists who comb through pieces of bones or chainmail buried in layers of dirt under parking lots to learn about ancient kings, stellar archaeologists use large telescopes to study the chemical makeup of ancient stars in hopes of understanding ancient supernovae and maybe even the very first stars. You might say that these first stars are the holy grail of stellar archaeology. And what we've learned from these ancient stars is truly astounding. Now, it's quite reasonable to think that nature would have worked down the periodic table gradually, starting with the light elements and slowly building up to the heavy ones. But these ancient stars, they tell a different story. By the time just the second or third generation of stars had formed, uranium was there. Uranium. Element number 92, the heaviest element found naturally on Earth. Even uranium made its first appearance in that first billion years after the Big Bang. And it was not just the uranium, but every element on the periodic table, every last one, made its first appearance in the very early universe. Now, we know this because we find the chemical signatures of uranium in those ancient stars. One of the most powerful tools in astronomy is called spectroscopy. The ability to take light from a star or some other distant object and then to separate it out into all its different energies. One photon, one 13 billion-year-old photon at a time. And as you can imagine, this requires sensitive instruments on some of the largest telescopes ever constructed. And you can think of these instruments as grand versions of Pink Floyd's Dark Side of the Moon. We decode the spectra of these ancient stars to reveal their chemical DNA. All of the small dark bands in the stellar spectrum on the right, there are hundreds of thousands of them in some stars. All of these small dark bands are due to the atoms and the molecules in the atmosphere of a star. And there, well hidden among the dense spectral forest of iron and cyanogen, there we find uranium. We find uranium on Earth in a mineral called pitchblende. And after extraction, the uranium is often formed into a heavy yellowish metal, uranium oxide, called yellow cake. And this bears resemblance to a certain brand of cupcake. And both have similar healthful qualities when ingested by humans. But what I haven't told you yet is where in the universe all that uranium is forged, or what the manufacturing process looks like. This whole business of creating heavy atoms by putting together light ones, that's called nucleosynthesis. Nucleosynthesis reactions require great amounts of energy. They don't occur under the ordinary conditions here on Earth. They don't occur in the cells in our bodies. But nucleosynthesis reactions are the basic way that stars like our sun generate energy. And it is this energy that sustains them throughout their lives. An opposite of nucleosynthesis is called radioactive decay. When an atom or particle is radioactive, it is unstable. And it eventually must transform into a different atom, particle, or a collection of particles. Now, radioactive decay can take many forms. And one form of radioactive decay is what powers the light that we see in supernovae. Not as they get bright, but as they fade away into the darkness. There are just a handful of basic rules that govern why it's so hard to produce heavy elements like uranium. These can be summarized, I think, as electric charge, neutrons, and what I call the element gap. So let's talk about uranium nucleosynthesis and why each of these three matters. Now, we all know the basics of the very first one, electric charge. Protons have a positive charge, electrons have a negative charge, and neutrons are electrically neutral. We all know that opposite charges attract, like the proton and the electron, and we all know that like charges repel, like two protons. The nucleus, or the core of an atom, is where most of its mass resides, in the form of protons and neutrons. So there are no electrons that permanently reside in the nucleus. So you can imagine that the nucleus of an atom has a very large positive charge, like the nucleus of uranium, for example. More than 99.97% of the mass of the uranium atom is in its nucleus. Only protons and neutrons, though. So the positive charge, the size of that charge, is proportional to the number of protons in the nucleus. And for uranium, which has 92 protons, that charge is quite large. So if you want to grow the mass of an atom, you have to add protons or neutrons to its nucleus. But if you try to add protons, those protons feel the overwhelming electric repulsion from the 92 protons that are already there. And the new protons just cannot get in. But if you use neutrons, they're neutral. They don't feel that electric charge. And the neutrons can just waltz right in if you point them in the right direction. Once those neutrons are in the nucleus, then some of them may be unstable, and they may transform into a proton, an electron, and an antineutrino. Now, the electron and the antineutrino escape that nucleus immediately, leaving behind the proton. And now that the proton is in the nucleus, it's perfectly happy to remain there, because there's another natural force that we call the strong force that only works on the small scale of the atomic nucleus. So that's one challenge. You need neutrons. The next challenge is finding those neutrons. Now, a free neutron, which just means unattached or unbound, a free neutron is itself not a stable particle. And left to their own devices, these bachelor neutrons will decay into protons, electrons, and antineutrinos. Neutrons have to be bound up in atomic nuclei to survive for more than just a few minutes. So, if you want to use neutrons to grow the mass of a particular atom, you have to have several things all happening at once. First, you need some reaction in the star that divorces these neutrons from the atomic nuclei that have housed them previously. Simultaneously, you need a different reaction to then wed those neutrons to the atomic nucleus that you're trying to grow. And if that all sounds rather complicated, yeah, it is. So that's another challenge. The third one is what I call the element gap. This is the long string of radioactive elements just a little bit lighter than uranium and thorium, element 90, its neighbor. The last stable atom before you get to thorium and uranium is bismuth, element 83. So if you're just going to add one neutron at a time to bismuth atoms, hoping to eventually get to uranium, you'd have to go through polonium, astatine, radon, francium, radium, and actinium, all of which are unstable. At the temperatures and densities that are common in stars, the reactions that do this just don't operate fast enough to overcome all those radioactive decays. So there needs to be another way, a fast way, a rapid way. This is what astronomers call R process nucleosynthesis. And the R stands for rapid. Some cosmic explosions add a burst of neutrons so quickly that the radioactive decays just cannot keep up with the neutrons. And that's how you bridge this gap. Those cosmic explosions might add so many neutrons that they transform light atoms like iron into the heaviest elements found in nature. Iron to uranium, and everything in between, and even some beyond in just 1 second. Gold, silver, platinum, cesium, cerium, and barium, yttrium, erbium, terbium, ytterbium, arsenic, mercury, radon, lead. Imagine the incredible energy that goes into all these reactions. It's unthinkable, and the conditions that do this are unlike anything any laboratory on Earth can ever hope to mimic. Now, imagine the incredible energy that would be released if you run the reactions backwards. The nuclei of heavy atoms were forged in ancient stellar furnaces, sealing off a portion of the energy of the death throes of a star into multitudes of minuscule time capsules. We found some of them on Earth. We tinkered with them in secret laboratories. We released from them trillions of neutrons in a nanosecond. We declared them to be, in the words of the former New York Times science editor and irrepressible optimist William L. Lawrence, mankind's transition to a new age, an atomic age. In less than the lifespan of one of our own species, we had gone from not really understanding why stars shine to controlling and even reversing the very reactions that accompany stellar deaths. And in doing so, we rekindled the flame of those explosions right here on Earth. Perhaps it was inevitable that one of our first tasks after doing so was devising a way to effectively blow up our neighbors. More than 50 years ago, right here in Pasadena, one of the most influential papers in 20th century astronomy was written. Now, the authors of this paper posed and then proceeded to answer a question. And I've repeated that question here for us. What has been the history of the matter on which we can make observations, which produce the elements and isotopes of that matter in the abundance distribution which observation yields? It was indeed a dark and stormy night. And it's a sentence worthy of Edward Bulwer Lytton himself. So let's recast this question in simpler terms. 140 characters or less. What is the origin of the atoms around us? Now, these authors were trying to explain the relative amounts of all the elements that we find here on Earth. And the R process was one way that they proposed stars might do at least some of this. This chart shows a modern version of what those authors were trying to explain. This is the distribution of elements on Earth, in the sun, in the solar system. The horizontal axis shows the atomic number, which element, basically. And the vertical axis shows the relative amounts of each element. Now, these measurements come from studying the composition of the sun or certain meteorites. Nearly all of the structure in this diagram, every bump, every wiggle, that can all be explained by the nuclear structure of atoms or the physics of stars. Here's hydrogen, element 1, all the way over on the left. Carbon, nitrogen, and oxygen, elements 6, 7, and 8 are here. I would not call you crazy for suggesting that the human body is comprised of more than 99% hydrogen, carbon, nitrogen, and oxygen, because these are 4 of the most common elements on Earth. Poor old uranium, element 92, is all the way over on the right. For every trillion atoms of hydrogen, there are almost 250 million atoms of carbon, almost 500 million atoms of oxygen, and less than 1 atom of uranium. Let's put this in perspective. Let's take every man, woman, and child on Earth today. There are about 7 billion of us. And let's give everybody a ream of paper, 500 sheets for each person. Among all that paper, you could cover the entire state of Kansas with it. That's how much paper that is. Among all that paper, only 1 sheet, 1 lucky golden ticket, only 1 sheet would represent the fraction of uranium atoms among all atoms on Earth. And remember what I said at the beginning of the talk. The first use of uranium atoms in nuclear weapons was found through the uranium-235 isotope, which itself makes up less than 1% of natural uranium. So, less than 1 square inch of that 1 sheet of paper among all the paper we've given away. 1 postage stamp in the state of Kansas. That's the fraction of uranium-235. And yet, there's still enough of it to inflict unimaginable terror. Where does uranium come from, though? We find it here on Earth. The truth of the matter is we still don't know, actually. Even now, 50 years after that, more than 50 years after that influential paper, we still don't know exactly where that R process happens, where that uranium is manufactured. Now, theory tells us that the demand for an explosive event with lots of neutrons, that implicates 2 good candidates. One candidate might be in the violent explosions that mark, in the winds of these explosions, that mark the death knell of stars tens of times more massive than our own sun. These explosions would have happened early and often in the universe, so that's a good candidate. Another good candidate might be in the violent merger of 2 neutron stars that are locked on a death spiral. This simulation shows a cutaway view of what might happen to those 2 stars as they collide with each other. This is exciting stuff, so let's take a look. As those stars collide, they fling out these long tails of neutrons. And the R process might happen in those tails. Maybe both the supernova and the neutron star collisions can work. Maybe there's something else we haven't thought of, too. But the models, and of course the astronomers who make the models of this, they've not yet come to a consensus on which one, if either, is right. I'm an observer. I don't make the models. So I don't have a horse in this race. But I'm convinced that it's going to take an unambiguous observational result to say definitively where the R process occurs. And this is an exciting time. And we've been making these observations for many years, and there's been progress, but we still lack that definitive observation. This is an exciting time because just this month, a team of astronomers at Carnegie and the University of Michigan shipped a new instrument to the Magellan telescopes at Las Campanas Observatory in Chile. That instrument is called M2FS, the Michigan Magellan Fiber System. I hope to use this new instrument to create a new kind of observational data set, one that might help us answer the question, where does the R process occur? Regardless of where astronomers like me say that the uranium actually comes from, we still find it here on Earth. And the curious thing is that both isotopes of uranium are ultimately unstable. But the uranium-235, the rare one, the one that's useful, I guess, for certain devices, that one decays 6 times faster than the uranium-238. So if you have a sample of uranium-238, it will be reduced by half after 4.5 billion years. But if you have a sample of uranium-235, it will be reduced by half after only 700 million years, 6 times faster. So the longer you wait after that R process event, the fewer atoms of uranium-235 you will have left in your yellow cake. And currently, that uranium-235 makes up less than 1% of all uranium atoms on Earth. But as we've seen, that 1% makes all the difference in the world. Without it, nuclear weapons may have never existed. Or maybe they would have been developed much more slowly in the open scientific literature as purely plutonium devices. If that 1% had been, say, 10%, then the uranium separation process could have proceeded much more quickly. And the first weapons could have been available in months rather than years. They could have been available long before the Nazi Party surrendered, long before the war in Europe was brought to a close. They could have been available long before the military and political leaders in this country who approved the funding for their mass production without consulting Congress, before they'd had a chance, at least in principle, to consider the moral and ethical implications of using such a thing. Scientists who were not affiliated with the American program may have independently and quickly learned how to make a sustained chain reaction in natural uranium. By the end of the Second World War, scientists in the United Kingdom, France, Germany, Japan, and the Soviet Union had all considered the possibility of a nuclear weapon. Only technical challenges prevented their rapid advent. So would those experiments have turned out differently if the uranium isotope mixture on Earth was just a little bit different? But if you go back in time, it was different. About 540 million years ago, at the beginning of the Cambrian period, when the diversity of multicellular life forms on Earth began to expand rapidly, at that time, the uranium-235 was about 60% more plentiful than it is today. But even that was already 4 billion years after the solar system and Earth had formed. When that uranium was produced in an R process event, sometime before the formation of Earth and the solar system, When that uranium was produced, the uranium-235 almost certainly outnumbered the uranium-238, perhaps by 50% or more. So we are left to ponder this question. If life on Earth had evolved at a faster rate, might we have developed the technology to create nuclear weapons when the uranium-235 isotope was more plentiful? And there's a corollary to this speculation, too. There's been a lot of interest in the last few decades in trying to detect signals from intelligent extraterrestrial life forms using radio telescopes like these and other methods. There's a well-known equation named for the astronomer Frank Drake that tries to estimate N, the number of civilizations in our galaxy that we might have a hope of communicating with. Now, this, of course, depends on many different factors. The rate at which stars form, the fraction of stars with planets, civilizations with technology, and so on. But the last term in this equation is not a rate. It's not a fraction. It's a length of time. It is the average length of time that a civilization maintains the capability of sending signals out into space. So let's think about this in terms of our own species. From the time our first wireless radio broadcasts were made in the late 19th century until the beginning of the atomic age, July 16th, 1945, on the remote grasslands of central New Mexico. In that time, less than one average human lifespan had passed. One lifetime. That's it. In that one lifetime, we developed for the first time ever to communicate around the globe and then to annihilate ourselves en masse. In that one lifetime, multiple countries at war with one another had stockpiled arsenals of nuclear weapons capable of eradicating hundreds of millions of people, leaving the unfortunate survivors back in a poisoned environment in the Ice Age. One lifetime. So, how many extraterrestrial civilizations out there might we be capable of communicating with? If we base this estimate on ourselves, as we so frequently do when looking for biomarker atmospheric gases in the atmospheres of Earth-like planets orbiting in the habitable zone around sun-like stars, if we do all of that, we may conclude that the number of extraterrestrial pen pals is distressingly small. And our story does not end without tragedy. Those individuals in the two cities in Japan, those whose homes were close to nuclear testing grounds or separation factories, those who were considered expendable by the bureaucrats. But as a civilization, we survived that first lifetime in the atomic age, and then another. Now, experts who are certainly not astronomers like me have concluded that there are something like 17,000 of these devices around the world today. Now, sure, we've developed other technologies besides the uranium fission that produce a similar result. Plutonium fission, hydrogen fusion, both of which took a few years to develop, and they're actually now much more common than the uranium. But we're faced with this dilemma. The uranium is here, and the principles for turning it into weapons of mass destruction are mostly public knowledge. Mercifully, we have not yet fulfilled Winston Churchill's prophecy that all those additional devices would just make the rubble bounce. we have made it this far. Perhaps we live in a universe that prevented us from annihilating ourselves while in a more primitive state of evolution. Perhaps that first lifetime or two after developing this technology is critical. Perhaps the silence of our galactic neighbors is telling. Or perhaps not. So where does this leave us? Stellar generations of long ago gave us the raw material for life, the carbon, the oxygen that we depend on every day. Fusion reactions in our own star, the sun, provided a steady source of energy so that life might develop here on planet Earth. Even time will convert warheads into radiation shields. But it takes a long time. So in the meantime, may we please find something better to do with our time and energy than just devising more ways to effectively blow up our neighbors? When you look at the stars, what do you see? Thank you.
Do you have any questions? I'm sure there must be some questions and or comments. It's not on there. Oh, yeah. Yeah, it's not.
I think you're on. You want to come up here?
Questions? Right here, Louis.
What makes detecting uranium in stars difficult?
Question is, what makes detecting uranium in stars difficult? Uranium is a very trace element. There's not much of it in stars either. So intrinsically, it's going to have a very small effect on the spectrum of a star that you see. That's one challenge. The other challenge is that those other more common elements in stars, iron and cyanogen, especially in this case, are much more visible, much more detectable, and they effectively wash out the signature of uranium. So at present, we have detected uranium in a total of, count them, 1, 2, 3 stars outside of our own solar system. It's a challenge.
There's a question way in the back.
How slow is a slow neutron as opposed to a fast one?
Question is, how slow is a slow neutron as opposed to a fast one? I have a question follow-up for you. I'm not sure which form of slow you're referring to. Are you referring to the ones that cause the chain reaction or the way that stars do it?
Cause the chain reaction.
Slow neutron in this case means one that does not by itself violently cause an atom to split just from the collision energy itself. So in the case of uranium-235, you can actually have, in principle, you could have a neutron of 0 energy. That's not quite right because you would never actually get into the nucleus, but very low amounts, keV, if that means anything. Very low amounts is a slow neutron, something that doesn't violently shake up the nucleus. That happens in uranium after it's in the nucleus for other reasons.
Other questions?
Said that the reaction, the R reaction in supernova, you mentioned happening in the outer winds and not in the internal blast.
Yeah, the question is referring to where in the supernova that R process might occur, in the outer winds as opposed to down inside in the core. It may very well happen in the core also, but if we're going to actually have any evidence of that supernova in the form of heavy atoms that escape, it has to be in the winds. the core of that supernova is going to be locked up in this compact remnant forever, effectively. It becomes a neutron star or maybe even a black hole. And anything that happens in there never gets out. So if you're going to eject that R process material back out into the universe where it can then form into new stars or do whatever, it has to be in the winds.
U-235 is so rare. Of all the nuclear weapons on the planet derived from 235, is that one of all of them?
Question is, since uranium-235 is so rare, are all the nuclear weapons on the planet derived from that, effectively? I'm not a weapons expert. My understanding is that the first weapons in the first few years were largely based on the uranium-235. And I think even the plutonium weapons that came later, very slightly later, were even, at least the first ones were initiated by a uranium-235 detonation in the core. Now, the details of that stuff has never been declassified. My understanding is that the other mechanisms, the plutonium implosion devices and the hydrogen fusion devices, are more compact, slightly. They're easier to engineer. And at some level, the uranium-238, which is what you turn in to get the plutonium, is much more common. So I think there's a myriad of reasons why the other kinds of devices are more common now, but certainly there must still be a few of the old uranium-235 gun devices around.
There was a question up here.
On an atomic level, what are the substantial differences between uranium-235 and 238? What are the differentiating factors?
Question is, what are the differences between between uranium-235 and 238 on the atomic level? They have the same number of protons, 92. The number of neutrons is different. And the difference that is relevant for this particular topic, the one that makes uranium-235 go boom and uranium-235 or 238 just fizzle, is the fact that when you turn 235 into the next heavier isotope, 236, it's slightly more bound up as 236. So protons and neutrons, when they're in the nucleus of an atom, they like to pair off. And they're slightly happier when they're paired off. So even numbers are preferred. So basically, when they're happier, they have a lower energy state. So when you convert 235 to 236, you gain that neutron and you get a little bit of energy out. And it's that extra energy that causes the uranium-236 to start doing this. And eventually, this separates. And that's how you get the two different atoms, the photons that give you all the energy in the explosion, and the neutrons that continue the explosion. That's the main difference relevant here.
You're suggesting that dimension is development. I'm not saying anything to those who develop. What does that say to you as a person trying to science?
Question is, what is the ethical statement to me at present, to say nothing of the scientists and those who did this many years ago? We can't put ourselves in their shoes. I would love to have as much influence as anyone who could actually bring any bearing on this kind of decision. I would hope that those who do have that influence have some restraint and understanding of what actually happens when these things go off. The implications of it, not just immediately in terms of the violence that's produced, but the long-term effects, not just locally where the explosion happens, but the long-term effects at the places where you manufacture them, where you test them, where you extract the uranium from the earth, and all of the ethical, it was a really messy ethical situation just getting the uranium out of the mines because of where they were located. In Turns out uranium's sort of located everywhere. It's not that rare on Earth in the crust in terms of finding it. You can still find it everywhere. It's just a very small component. So know what you are doing. I think that's, have compassion.
One last question. Regarding the dark process, besides supernova, what other astronomical phenomenon are we use to study our see how it increases?
Question is, what other, if I have this right, what other astrophysical phenomenon can we use to study the R process? Besides supernovae. What you'd really like to do is study the events where it's happening itself. That's a challenge for other reasons that we can talk about later. So what you might do instead is look at where the R process material ends up, what its distribution is in different environments in the universe. Where do we find it? Where do we not find it? And one idea that I have that I'd really like to pursue with this new instrument is to study star clusters. We can characterize these things in great detail, and there's lots of stars there. And what's so cool about a star cluster is that all those stars formed at basically the same time from basically the same ball of gas. Not quite on either, but almost. And if you can characterize how that R process material is distributed within that cluster of stars, maybe it's a little more over here, a little less over here, whatever that ends up being, that tells you something about when that R process material got put into that ball of gas that turned into all those stars that we see today. No one's done that. There are other ways to do this too, but that's an underappreciated one, I think.
All right, I know there's other questions. I'm sure Ian will be happy to hang out for a little while and answer questions, so feel free to come up. I want to thank you again for coming. We hope look forward to seeing you in the future. If you're not on our mailing list, the Carnegie mailing list, please sign up. We'll have an open house this October. You can come and check out our facility and lecture series sometime next year. Thanks again for coming.
Thank you.